Hello. Um, Welcome to another class of CS360. So today we will cover context-free grammars. Um, so, um, um, so context-free grammars and context-free languages. Um, Context-free languages are a generalization of or a more general class than regular languages. Um, and they're defined in terms of these things called context-free grammars, um, which are sort of motivated by linguistics. But we won't really do any linguistics in this course. So really the idea is that we have a set of variables, um, a variable like s, and we have these rules that tell us so let's say our variables are s and x and y, and we have rules that tell us that the variable s can turn into some sequence of variables. Um, so we have multiple rules for each of the variables, you know, um, and then other than just one variable turning into a sequence of variables, a variable can also turn into um, alphabet symbols. So we can have x turn into 0 here, for example. And we can have y turn into 1, y1, for example. So we can combine um, uh, kind of these symbols, these alphabet symbols like 1 and variables like y. Okay, so more generally, rules are going to have the form one variable like x or some variable, and then an arrow, and then a string, and the string will have characters that can either be alphabet symbols or variables. So uh, well, let's put a string w here, and then w is going to be some string in the way we put it in the notes in sigma union v star, where sigma here is going to be our alphabet. So like sigma might be 0, 1, this at 0, 1, okay? And v is our set of variables for this context-free grammar. So v might be this set here, okay? So then w is a string that includes both things from sigma and things from v potentially. And a rule is a thing that looks like this, okay? So, whoops, so this is a rule. So, okay, so in general, a context-free grammar, which we denote G, is going to be specified by these four things. A set of variables V, okay, uh, an alphabet sigma for the symbols, a set of rules R, okay, and where each rule has the form that we described, and also one special start variable, which we usually denote S. Okay, so here S is a variable, so S is in V. Okay, and then R contains, it basically contains strings of the form X, arrow, W, strings like this, where, X is in V, X is a variable, and then W is in sigma union V star. So W is some string that has both potentially both alphabet symbols and variables. Okay, and so the interpretation of a context-free grammar is that the context-free grammar basically allows us to generate strings, and the way it generates strings is that well, okay, so let's just do a concrete example. Suppose I have a context-free grammar that says S. It has the rules S arrow X or S arrow Y, or and also the rules X arrow 0x Y arrow 1y, Okay. And then let's say x can also become epsilon and y can also become epsilon. Okay, so here R is going to be this collection, this set of rules. Okay. So when we have such a set of rules, we can generate a string using it by starting with the start variable s and basically picking rules to use. So we can say, okay, from s, we are going to go to, we'll use a double arrow for going to a new string. So from s, we will go to x, and from x, we will go to 0x, and from 0x, we will go to 0x, and from 0x, we'll go to 0x, and then we will go to 0. So what happened here is that each time I pick a rule to use, so over here in the first transition, I picked this first rule over here, okay? And then for the next transition, I'm picking a rule. So in this case, I pick this one. And what's going on is that I substitute a variable each time with whatever it turns into on the right-hand side. So basically, each time I have such a string, I pick a variable in it, like I pick the x, and I substitute what's on the right-hand side of a rule. Okay, so I keep doing this. In the end here, I use this rule here. X goes to epsilon. So I replace x with epsilon, and I get the string 0, 0, 0, right? So the so this is called a derivation, this sequence. And note that I had many choices of how to get a derivation starting from s. So I can also derive other strings. So I can, for example, derive the string 1, 1. You can see if you can see how to do that here. I would start with s going to y, and then y going to 1y, and then again using the rule y going to 1y, and then y going to epsilon. So I can derive other strings. And when the strings that I derive are in sigma star, okay, then we say that this context-free grammar generated that string in sigma star, and the set of all strings it can generate is called the language of G. So L of G is equal to the set of all strings that G can generate. And then we always start with the start variable s. Okay, so s is the thing that's specified here. So it's it has to be given as part of the definition of the context-free grammar G. What is the start variable, basically? Okay, and so let's just do another example here. So we can have rules that involve multiple variables on the right-hand side. So it's okay to have rules that go as goes to, for example, 0s1. This is a valid rule. We can also have s going to epsilon. So when we have multiple rules with the same variable on the left side, we will often just put them next to each other with a bar denoting or. So we will actually we'll put it like this. S can become either 0s1 or epsilon, you know, or let's also allow it to become ss. Okay, so just for example, so here s can become a string of 2 s's. So now we can use we can transition. For example, we can do s going to ss. Okay, and then we can replace the first s here. We can replace it with by using the first rule, this rule here. So we can go 0s1 and then s. So this 0s1 replaced the first s over here. Okay, and then we can keep using rules. So for example, we can replace this s again with another 0s1. So we get 0, 0, s, 1, 1, s. Okay, and you know, and we can use any rules wherever we want. We can replace this with epsilon now. So we get 0, 0, 1, 1, s. We can replace that s with ss again. So we get 0, 0, 1, 1, ss. Okay, and we can keep going. So we can replace this S with 0S1. Okay, and let's just replace these two with epsilons. So actually, let's replace the right-hand S first. Why not? We're allowed to replace any variable we want. So let's replace that with epsilon. We get this string. And finally, we replace this S with also with epsilon. And we will get 0, 0, 1, 1, 0, 1. Okay, so this final string is generated by this context-free grammar that we wrote up here. Okay, so it generates this string, for example, among many strings that it generates. Okay, so this is basically the key point of a context-free grammar. And note that each variable substitution, so each variable, what you replace it with, you can replace it with anything you want and using any rule for that variable. Okay, but the variable sort of doesn't know its context. That's why it's called a context-free grammar. The rules of what S can be replaced with do not depend on what's to the left or right of S in our string. So like this S can be replaced by anything according to these rules, but those rules don't depend on whether there's a 0 to the left of S, okay, or a 1 to the right of S. They don't depend on the context of S. So, you just blindly take a variable and pick a rule to replace it with. Okay, and you have many choices. And because you have many choices, then you can generate many different strings. And any string you can generate is in the language of that context-free grammar. And so the language contains exactly the set of all strings you can generate in this way. Okay, so each context-free grammar defines the language. Now, some context-free grammars, so if I have a new context-free grammar that just has a stupid rule like this, these S's, you can never get rid of them. They never become epsilon. So you can never generate any string in sigma star. You cannot even generate the empty string. So if you only had this rule, so imagine you only had this rule, okay, then you cannot generate any string in sigma star. So like if G was the grammar that only had this rule, then L of G would be the empty set. It will have no strings that can be no strings within sigma star that can be generated. Okay. All right. So that's the basic idea for context-free grammars. Context-free grammars are more powerful than regular expressions, for example. They can generate strictly more languages. So for example, here is something that you can do with a context-free grammar that you cannot do with a regular expression. You can just do this, okay? And this will give you the language. So if G is this context-free grammar, then the language of G will be 0 to the n, 1 to the n, okay? So you can kind of easily convince yourself of this because you can apply the first rule any number of times you want to get n zeros and n ones, and then you can apply the second rule basically and turn S into epsilon to remove S and get a string in 0, 1 star. Another kind of classic context-free language is the language of balanced brackets. So here our alphabet is going to be these brackets. So our alphabet is going to be open bracket and closed bracket. Okay, and then we want all the balanced brackets. So like this, this will be balanced. This string will be a string of balanced brackets, but this is not, right? Because there's this unclosed pair here. And you can generate the string of all balanced brackets, or sorry, the language of all balanced brackets with various context-free grammars. One simple way to do it is to just, you allow S to either go to SS to basically say the two balanced bracket strings are allowed to be next to each other. So it's okay to have a balanced bracket string on the left and another one on the right, okay? Or you can have brackets around a balanced bracket strings. string. Okay. Or you can have the empty string, which is a valence bracket string. So these rules turn out to be enough to generate all the strings of valence brackets, as shown in the notes, I believe. Okay, so later on we will see more about the power of context-free grammars, and especially the fact that they can generate any language, any regular language can be generated by some context-free grammar. And we will also see kind of a machine called the push-down automaton that captures the power of context-free grammars. And so they sort of represent a computational model that we'll encounter later. All right.